Hello grade 12s and welcome to this video from the answer series. In this video we will solve problems involving work done by a pump and hence find the power of the pump. Many parts of South Africa have access to very little surface water, but then we are able to pump groundwater to the surface. The water has to be lifted from a certain depth, giving it more potential energy. It also flows out of the end of the pipe with an exit velocity, giving it some kinetic energy. To find the power, we just need the mass pumped every second. For example, if 1.5 kilograms of water is pumped out every second, then we can find the change in potential and kinetic energies. Both are assumed to be zero to start with. The borehole is 40 meters deep, and the exit velocity is 10 meters per second. So the amount of energy transferred is 663 joules. Because this happens every second, the power is 663 watts. Devices like pumps are designed to achieve a certain maximum power output. The maximum power depends on the energy source, the size of the moving parts of the pump, and the volume of the pump cylinder. When we know the operational requirements, we can calculate the minimum power required. A required volume of water must be lifted at least a certain height and leave the pump at a certain speed each second. The applied force of the pump on the water is a non-conservative force, so this equation can be used. Here is a question with requirements for minimum power. The borehole is 40 meters deep, and the required water output is 500 kilograms of water per minute, with an exit velocity of 5 meters per second. The amount of work done on the 500 kilograms is given by the equation for a non-conservative force. The water was standing still at the bottom, 40 meters below the surface. It was lifted 40 meters and gained 196,000 joules of potential energy. It leaves the pipe at 5 meters per second, so it gains 6,250 joules of kinetic energy. The time interval is 60 seconds, so divide the work done by the time taken to get a minimum power of 3,370,83 watts. Here is a question that starts with the maximum power and asks for the greatest depth possible. The power maximum is given as 40 kilowatts, and the required output is 250 kilograms of water per second with an exit velocity of 8 meters per second. In this calculation, start with the power formula, and the work done will be 40,000 joules per second. If the water leaves the pipe at 8 meters per second, then the increase in kinetic energy is 8,000 joules. The remaining energy, in other words, the rest of the 40,000 joules per second, is available for an increase in potential energy. Once all the substitutions have been done, the height works out to be approximately 13 meters. Now it's your turn. From the 3-in-1 study guide, do question 3 on page 161. The model answer is on page 169. From the 2-in-1 study guide, we have an intriguing question about an investigation of solar-driven pumps. They use solar energy to do the work of pumping water. The test specifications are to pump 50 kilograms of water from a depth of 80 meters. The questions that follow test our understanding of a scientific investigation. Let's see what the data looks like. There are 4 repeats with each pump, and the time taken is measured in seconds for each repeat. The questions ask about experimental design, the variables, and analysis of the data. Read through the questions. Besides the variables, there's a question about precision, and finally, you have to give a recommendation for which pump you would install. Note that in question 8.6, you are calculating maximum power assuming a zero final velocity. Then in question 8.7, you are calculating the speed of the water based on minimum requirements of 50 kilograms of water every half a minute. Question 8.8 is similar. Here the minimum requirements are 50 kilograms of water from an 80-meter deep borehole at a 5 meter per second exit velocity every 90 seconds. Pause the video now to answer these questions, then play again to compare your answers to the model answer. It is not often that time is a dependent variable. In this case, it depends on which pump is being used. To keep the comparison fair, each pump performs the same test, which is to lift 50 kilograms of water, a height of 80 meters. However, there was one variable that they overlooked, and that's the amount of sunshine available from the sun. Pump C got less solar energy, so it cannot be part of this comparison. However, all 3 sets of readings are equally precise, as they are all to 1/10 of a second. Pump A's tests are not as reliable. Reading 2 is nearly twice reading 4, which is a very large spread in physics. As a result, Pump B is the recommended pump. We use the definition of power and the change in potential energy to calculate the average power of pumps B and C. In this way, we find out that pump B is more powerful than pump C. Now we run pump B at that power level for 30 seconds. The extra joules of energy are then converted into kinetic energy, and the final speed of the water, the exit velocity, is 12,2 meters per second. Here we determine the minimum power required to meet specifications of 80 meters of lift and an exit velocity of 5 meters per second. We can use the formula for the non-conservative force, where the non-conservative force is the work done by the pump, to find the changes in potential and kinetic energy. Divide that by the amount of time, which in this case is 90 seconds, and we get a minimum power rating of 442,5 watts.
If you found this video useful, give it a like and subscribe to our channel so you don't miss any new episodes. Follow us on Instagram or Facebook to stay on top of the latest TAS news and launches. So that's it for now from The Answer Series, your key to exam success.